De Broglie waves, uncertainty, and atoms. Physics 1161, Pre-Lecture 29. De Broglie waves, uncertainty, and atoms. Sections 30.1 to 30.7. 1. Compton scattering. This experiment really shows photon momentum. Incoming photon plus 0 equals outgoing photon plus electron. Electron at rest. Outgoing photon has momentum p and wavelength. Incoming photon has momentum p and wavelength l. Recoil electron carries some momentum and k. Energy of a photon. De Broglie waves. So far only for photons have wavelength, but De Broglie postulated that it holds for any object with momentum: an electron, a nucleus, an atom, a baseball. Explains why we can see interference and diffraction for material particles like electrons. Comparison: wavelength of photon versus electron. Say you have a photon and an electron, both with 1 electron volt of energy. Find the De Broglie wavelength of each. Equations are different, be careful. Photon with 1 electron volt energy. Big difference. Electron with 1 electron volt kinetic energy. Solve for Heisenberg uncertainty principle. Rough idea: if we know momentum very precisely, we lose knowledge of location, and vice versa. If we know the momentum p, then we know the wavelength, and that means we're not sure where along the wave the particle is actually located. L. Y. Heisenberg test: P equals P sinc di equals W equals L slash sinc. Use De Broglie L. Screen. Number of electrons arriving at screen. W. P equals P sinc. P. Q. P. Q. Electron beam. Di equals W. Equals L slash sinc. Y. X. Use De Broglie L. The uncertainty in pi is PHW. Electron diffraction. Electron beam. Screen. Number of electrons arriving at screen. W. X. Y. Pi. Electron entered slit with momentum along x direction and no momentum in the y direction. When it is diffracted, it acquires a pi which can be as big as hw. The uncertainty in pi is PHW. An electron passed through the slit somewhere along the y direction. The uncertainty in y is dw. Electron beam. Screen. Number of electrons arriving at screen. W. X. Y. Pi. If we make the slit narrower, decrease W equals di, the diffraction p gets broader, p increases. If we know location very precisely, we lose knowledge of momentum, and vice versa. Remember earlier we saw that a particle whose momentum, and therefore wavelength, is known precisely is very uncertain in position. Rutherford scattering. Scattering He++ atoms off of gold. Mostly go through, some scattered back. Alpha particles equals He++. Only something really small, i.e. nucleus, could scatter the particles back. Atom is mostly empty space with a small, r equals 10 to 15 meters, positively charged nucleus surrounded by cloud of electrons, r equals 10 to 10 meters. Nuclear atom, Rutherford. Large angle scatterings. Nuclear atom. Classic nuclear atom is not stable. Electrons will radiate and spiral into nucleus. Need quantum theory.